Hello, my name is Ievgen Iosifov, and today I'm going to present the results of our work on techniques comparison for natural language processing. The main task of our research were to propose an algorithm or framework to make architectural decisions on which techniques and architectures to use based on business need and data or resources available. In order to come up with such algorithm, we review and compare main deep learning techniques and architectures to solve natural language processing tasks, their limitations and main parts. Our current work focused and based on a number of breakthrough papers in natural language processing area related to deep learning techniques and backpropagation. Next main building blocks and concepts of nowadays natural language processing were covered in current work in order to provide an intuitive understanding of the purpose and limitations to use them effectively with the algorithm. These blocks are embedding layer, recurrent architecture, including RNN, GRU, and LSTM, encoder-decoder architecture, Bi-directionality, attention, and self-attention, so-called transformer. For a neural network to be able to complete its task, there is a necessity to provide a numerical token representation of input sequence. There are many techniques to represent token, starting from simplest one-hot encoding up to complex contextual embeddings. Nowadays, almost any natural language processing algorithm working with text uses different type of word embedding techniques to represent such token. Word embedding technique create vectors out of tokens. Vectors comparison results in token semantic similarity. Hence, different words with similar meaning will have similar vectors, and different by meaning groups of words should be separable in vector space. Recurrent neural networks, or RNN, is the main starting point in the natural language processing area. Deep neural networks uncover a second life for RNN. Strong RNN advantage for natural language processing area is that RNN can store the conditions of all cells that were processed language data before. Hence, current cell output incorporates information of all previous cells as well as information of current input token. The encoder-decoder architecture consists of two RNNs. The encoder encodes all input sequences and store all information in context or so-called encoder vector. In simplest architecture, last hidden state is used. That is the input to decoder, which decodes by result predictions. There are few variations of RNN cells architecture. Main task of each cell is to encode current input token. RNN do this differently in different architectures by using gates to decide which information of previous or current cell to preserve and which to forget. In LSTM, the most commonly used nowadays RNN architecture, there are three gates: forget gate, input gate, and output gate to update output hidden state of current cell. The main drawbacks and limitations of RNN networks, including GRU and LSTM, is problem with long-range dependencies inside the sequence. Hence, each step decoder uses all encoded input sequence without paying attention to relevant part of the sentence while decoding a particular piece of sentence. Hence, accuracy limitation. Another limitation is absence of parallelization. Hence, limitation in amount of data to be used to train. In order to solve the long-range dependencies problem, there were some enhancements proposed. One of the main concepts here is the concept of attention, which significantly affects the current state of NLP area. An idea of attention is that at each step the decoder focuses only on some particular part of source input sequence, not on all sequence. Another important enhancement to RNN, not related to long-range dependencies problem, was bidirectionality. Intuition here is simple. In order to better encode current word, it is better to know what is after it. For example, I like Apple products versus I like apple juice. Word apple should have completely different embeddings here, because the context is completely different. And bidirectionality can solve this. Last breakthrough in natural language processing area is the transformer, a novel neural network architecture for language understanding based on self-attention mechanism. The main novelty here was that to build a language model, there is no need for any recurrent or convolutional layers at all. Solely self-attention and feed-forward layers are enough. The transformer includes a lot from what we've described before: bidirectionality, encoder-decoder architecture, attention, and in additional parallelization, at least on feed-forward step, which is most expensive, by completely replacing sequential computation, RNNs or convolutional-based to attention-based network. Transformer can be trained on unlabeled data and on much more data. For example, last GPT-3 model was trained on nearly 1 trillion words. Despite accuracy of transformer architecture, it is have significant drawback. It is very computationally expensive. To partly solve this problem, there are more and more often practiced to train once and fine-tune transformer-based model. There is some limitation here. Domain. Tokenizer for pre-trained models is limited to some vocabulary, for example 30,000 words. It might be different for different models. Hence, for some domain, it is just cannot be used as effectively as for another, for example medicine. As we can see, there are a lot to choose from. Hence, we proposed algorithm to make our architectural decision. Main input here is from top to bottom. We will start with domain. As we have described before, for some domain, you just have to train your own model from scratch on your own data. See right part of the picture. Here, decision would be made on availability of labeled data and availability of resources. Transformer for sure will give better accuracy. On the other hand, if your domain is common, you can leverage great pre-trained transformer-based models. Here, limitation is either pre-trained model can be fine-tuned for your specific task or not. If it can, great. You just need to choose one that cover your task, as most models comes in partly transformer architecture. For example, encoder like BERT, etc., which can be used to solve tasks like named entity recognition, classification, or decoder-like architecture like GPT, which can be used to generate text or predict next word. If your task cannot be solved with pre-trained model, question here would be if you have labeled data or not. Hence, you will proceed either with classical RNN architecture, for example LSTM with attention and bidirectionality, or will use advanced ELMO or ULM-FIT if you do not have labeled data. In future, we are going to solve the problem of sentence segmentation of raw, unpunctuated texts to make video and audio transcripts available for NLP task as training input. Let's go to the conclusions. As we can see, all current state-of-the-art techniques and architectures are based on deep learning, backpropagation techniques. And with so many techniques and architectures, it is easy to shift focus from business tasks to techniques evaluation, comparison, etc. We proposed algorithm to choose techniques to make it possible to decrease time to market for business tasks and need. Thank you for your attention.